All right, so now we have a skater who has an initial speed of, so let's just start drawing stuff here. We got a skater, all right, and skaters skate. Da, 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 you know, do that little hands behind their back thing. All right, so here's the skater. Got an initial velocity of 7.6 meters per second. Here's our frictionless ice. You can tell. You can tell that's frictionless because it's blue. All right, frictionless ice. Okay. There we go. All right, frictionless ice. And then the question is, air resistance is negligible, so we don't have to worry about any resistive forces other than friction. Coefficient of kinetic friction is, mu is, it's not frictionless ice. Mu is equal to 0.100. Okay? Now, wait a minute. Does it seem like we need to know the mass of the skater? Why would we not need to know the mass of the skater? What do you imagine is going to happen? It is going to cancel out, okay? Of course it's going to cancel out, because think about it. What do we have? We have MA, right? Force MA, and we got forces equal to mu times mg. Those m's are going to cancel out, okay? You could say, well, what if the skater was bigger, at least twice as fat? Well, bigger. And so wouldn't it take twice as much force to slow him down? Yes, it would over the same distance, right? But the thing is, he's got twice as much force because he increases the normal force by a factor of 2, and thereby the friction by a factor of 2. And since friction is the net force, you double the net force, and you double the mass, you keep the acceleration the same. Okay? So, here's the story. We have, first of all, the question is, what is the deceleration? Even though we don't like that term, it means, what is the acceleration in the opposite direction of the initial velocity? We'll say initial velocity is positive, so our acceleration should turn out to be negative, correct? All right, so we know that acceleration, let's see what we got. We got V naught, we got V final. What's V final? 0, coming to rest. Acceleration is equal to, ooh, we don't know, do we? All right, and we have time or distance. It's asking for distance, isn't it? Yeah. Doesn't ask the distance it's going to be? All right, so we'll call it delta x is equal to we don't know. All right, so we got a problem here. We have 2 unknowns, too much stuff. Is there any way that we can bridge this gap, this chasm of ignorance? How about if we use Newton's laws and try to figure out, what was that? All right. Sometimes a good choice. Sometimes never mind is a good choice. All right. So what about the net force acting on the skater? All right. Now we're going to go to Newton's laws. We have normal force. We have mg of the skater. And if this is V naught, then what direction is our friction acting? To the left or to the right? To the left. All right. And this is kinetic friction. Got that? All right. So the net force is going to be equal to ma. And the net force is going to be equal to, from our free body diagram, anyone? Kinetic friction, right? Acting in the negative direction. So net force is equal to negative kinetic friction. Putting these equal to each other, we get A is equal to, we're going to get negative kinetic friction over M. You guys okay with that? I skipped the step where I just set them equal to each other, then I divide through by m. All right, but let's take a look. We have a situation where the normal force is going to be equal to mg, right? We've got a horizontal surface, no vertical acceleration, no extra forces in there to complicate things with their components and their crying. Oh, I'm sorry, I'm thinking about children. All right, so we got negative force of kinetic friction over m, so this is going to be mu kinetic times mg divided by m. Look how that works out. Acceleration is going to be equal to mu k times g in the negative direction. Negative mu k g. All right? That's our acceleration. So now, are we going to calculate that? Nah, we're just going to stick it in the expression up here. So now we know acceleration is equal to negative mu k times g. Now we have 3 things, and we could solve for the distance. All right, well, actually, part A, it did ask us to solve for the deceleration, didn't it? So we would solve for that, and what was mu k? 0.1, right? So it would be 0.1 times 9.8. So it would be equal to negative 0.98 meters per second squared. All right, but we're not going to plug that in up here. That is one of the answers. That is one of the answers that we're asked for, but that's part A. Okay, that's part A. We know that that's not the real question. They're just stepping you through to the real question, which is, how far is he going to go? Well, delta x, well, let's do this way. What equation do we have here? What's missing? Time, so it's the eternal question. The eternal equation. All right, so v squared is equal to v naught squared plus 2a delta x. That's in general form, but we got to remember some things here. What is final velocity? All right. And what about acceleration? It's negative. Okay. So we're going to have 0 is equal to v naught squared minus 2. And what was our acceleration? Negative, well, let's do plus. Negative mu g delta x, and it's mu kinetic. I'll force that in there a little bit. All right. So I'm going to copy this expression right here and bring it down here where things aren't so sloppy. And we will be able to paste it, and we can work with a little more clarity here. All right, we are trying to solve for what? The distance, correct? All right, so delta x is going to be equal to, this is all negative right here, right? That's all negative. So delta x is going to be equal, put that on that side, then so it's going to be v naught squared over 2 times mu k g, not negative because we added that to each side. Right? Plus, it wouldn't make sense to have a negative distance. Okay? V naught squared over 2g, that kind of sounds like a max height problem, doesn't it? Isn't it weird how things start to take the same shape? You sort of recognize things that happened before. Remember, v naught squared over 2g was how high a projectile would go if it was fired straight up at v naught? All right, so v naught was equal to, what was it, 7.6 meters per second? Or 6.7? 7.6 meters per second, quantity squared, divided by 2 times 0.1 times 9.8 meters per second squared. Uh-oh, you know what's coming when I pick up the green pen. Dimensional analysis. All right, so we got meters squared over second squared divided by meters per second squared. And this goes ya. Whoop. This goes ya. This goes ha. And one of those, and we end up with meters. Yay, because we wanted meters. We're going to delta x. All right, so we get delta x. Anybody work that out for me while we were 2.9 meters. Delta x. What? 29? Oh, we forgot to, what happened? Off by an order of magnitude. That's significant, huh? All right, so delta x is equal to 29 meters.
Was that right?
I think the 2.9 you forgot to divide through by the 0.1, which multiplies by 10, right? Okay, so there you have it.